Hello everyone, how are you? How's everything? I hope you're having so much fun with your families. And also, I hope that you did have some time to go over the previous lecture, which was about the Fourier series. And also, I hope that you did have some time to go over the example that I solved for you and did the exercise that I asked you to do. So now, today, I'm going to talk about the properties of the Fourier series. It's the continuation of what we did last session, and these are the properties of Fourier series. What do I mean by the properties? These are some pretty simple things that you need to know about any operation. Here, where our operation is to transform something into the Fourier series, like transforming x of t into AKs, we're just going to find out what are the properties of this transformation. For example, linearity is very obvious. If you are showing x of t with AK and y of t with bk, a linear combination of these two, it means ax of t plus by of t, would also be valid in the Fourier domain. So ck will be a of k plus b of k, where a of k was the Fourier series coefficients of x of t, and bk's were the Fourier series coefficients of y of t. No, this was stating I was stating the obvious. This time shifting property, this one is probably the most important property amongst all of these things that you need to keep in mind. It says that if your signal x of t was shifted by a value t0 in time, your coefficient ak will become e to the power of minus jk omega naught t naught ak. It means a t naught shift, t0 shift in time domain will multiply an object to ak. What is this object? Is e to the power of minus jk omega naught t0. This t0 is coming from this shift. As simple as that. That's it. But this is very important, as I said, because we will see this time shift a lot along the way. The third property, this is also another obvious thing, the time reversal. If we know the Fourier series coefficient of x of t, then the Fourier series coefficient of x of minus t will simply be a of minus k. I guess it's also obvious. The time scaling is pretty interesting. If you are multiplying the time by a constant, like if you, instead of x of t, you want to find the coefficient of x of ct, it's interesting to know that the Fourier series coefficients, they won't change. They stay the same. Just stay the same. So if the Fourier series coefficients of x of t is ak, Fourier series coefficients of x of ct is also ak. Once again, the Fourier series coefficient of x of t is equal to the Fourier series coefficient of x of ct. Both of them are going to be ak. The next property is about the multiplication. This is an interesting one. And you're lucky because you just learned about the convolution right before the subject, right? Here you will see that y convolution is good. If you have two functions in time domain, x of t and y of t, imagine that you are showing the Fourier series coefficients of x of t with ak, and you're showing the Fourier series coefficients of y of t with bk, the multiplication of xt times yt will become a new function. This new function can be indicated with a new Fourier series coefficients. Let's call them hk. This hk is the convolution of this one and that one. How? You see, you remember the formula of the convolution, right? This is exactly like that. Like you see the sigma from minus infinity to infinity of ai b of k minus I. just keep it in your mind, okay? We might not use it a lot here, but just for your information, this is a very good point to know it as general information. The conjugation is also a very obvious thing, because you know what is the conjugate, right? The conjugate of a plus jb in complex numbers is a minus jb, right? So here it says if x of t was indicated by ak as the Fourier series coefficients, the Fourier series coefficients of the conjugate of x of t is going to be conjugate of a, but for the minus k, which makes sense again, because look, in the conjugate pairs, you see only the imaginary part becomes negative. The conjugate pairs, if the complex number is a plus jb, the conjugate is a minus jb. Only the imaginary part is becoming negative. That's why here you see a becomes conjugate, but on the is for minus k. This one was also mainly for your information. Look here, there is a table that we usually give you this table in your exams. All the information that you need are listed here. All the properties of the Fourier series. Look, properties of continuous time Fourier series. The linearity, the time shift, the frequency shift, the conjugation, time reversal, time scaling. The frequency shift, we didn't mention it over there because it's actually the easiest thing, okay? How? Because if you remember, we said if we shift the time with t0 in Fourier series, you will multiply it by e to the power of minus j blah blah blah, okay? Here, if you multiply your x of t by e to the power of j blah blah, in the Fourier series coefficients, you're just having a k minus m. Here, m was the coefficient of omega naught, like 2 pi over t is omega naught, right? So e to the power of j m omega naught t, it means the frequency is multiplied by omega naught. It means that your Fourier series coefficient is going to be having m deducted from that. If m was 2, your ak's will be ak minus 2. Right? For example, let's say if your a0, like for example, let's say your a5 of a function of e to the power of j omega naught t, for example, if it was a certain value, let's say it was 10, and a3 was 2, if you multiply your x of t by e to the power of j m omega naught t, your a3 is going to be the coefficient of the previous one. Like, it's actually a pretty obvious thing. That's why I didn't. When you use the rule, if you use the theorem, you will also, this is also very easily provable because you're actually multiplying this by an exponential thing. Because the whole idea was to write the function as sum of some exponentials. Now another exponential is being multiplied. It means the powers are being deducted. It's as simple as that. So you're going to have this table anyways, okay, with you. So no big deal. You're going to have it during any exam, and you have all the properties in front of you. There are some other properties that are also interesting, like differentiation. Differentiation in the time domain is simply multiplying the Fourier domain by jk 2 pi over t, which is jk omega naught actually. Which is actually, it's very easy. Multiplication and integration, the Fourier series makes them very easy for you. So, the main thing that we need, because again, we want to cut to the chase, the main thing that you need is the time shifting, I'm telling you from now. Time shifting, and of course, we're going to use the linearity a lot. Let's go over this simple example over here. if you have AK equals sine of k omega t1 over k pi, where t1, as you see here, t1 is capital T over 4, okay? And A naught is 2t1 over t, okay? 2t1 over t. So what is going to be gt, which is x of t minus 1 over 2? So we have one time shift, and also we deducted the constant. This constant, of course, is going to be deducted from A0, right? Because A0 is the constant here. Always A0 is the constant part. So in the final answer, your constant is going to become A0 minus 1 over 2. Your x of t minus 1 is going to be the same AK multiplied by, yes, you're guessing right, e to the power of j blah blah blah. AK e to the power of j blah blah blah. Done. See, it's as simple as that. The rest of the things over here, you really don't need to worry about them. I will tell you later on, just for general information, what is filtering. You already have some information that what is filtering, and here are just some basics about like what is a high pass filter, what's a band pass filter, what's a low pass filter, and it's how do we apply them. These are frequency selective filters, of course, and how do we apply them on the functions, which is no big deal, and actually we don't need them for the moment. All you needed to know were these properties, and remember, you have the table with you, and remember, you should be pretty handy applying the time shift. Thank you very much. Have fun. Take care. I'll see you soon.